Good morning. I would like to present forensic aspects of deepfakes. So this is a short presentation of 5 minutes, and I will shortly go through it. Nowadays, it's quite easy to make a deepfake. So you can download Deepfake Lab, which is freely available on the internet, and make your own deepfake. Or if you don't have the computational power, you can also use Google Colab to make those deep fakes yourself. So they will combine two faces in one person, and then you can speak with another voice and pretend to be another person. So there are many examples available. Many are also with presidents. You can find many of those examples on the internet. And one of the issues is that in court, people might say, no, it was not me, it was a deepfake. And then you have to examine if a deepfake was made. We see also that it's quite easy to make an audio deepfake. So with 5 minutes of training data, it's already possible to make a rather good deepfake of the audio, some voice cloning. So it's known for years that this is possible. One of the issues there is, of course, you need also to use the same stopboard as the normal person would use. So this is something to consider when making a good audio deepfake. There are many best practices in the world on finding deepfakes. So I will not go into detail to all those parts, but you will find best practice guides of image authentication of SwigDE, SwigIt in the past. You can detect it, of course, on the metadata, but that's easy to spoof with the photo response non-uniformity. So that's a kind of fingerprint of the sensor that might work. You can try to detect the image creation or some kind of staging, and some continuity issues. That's done manually. If we look into peer new analysis, we did this in the past, and in the past it worked quite well, so using the fingerprint. But if you don't have the camera, it does not work that well anymore. So unfortunately, this method is working less than 1 year ago. So we see that the algorithms for making deepfakes are getting better. So the newest detection methods, at least which were new a few months ago, they are often image-based. So that's something we see that there could be also a better way of detecting it by making it video-based, so based on the compression schemes, etc., that are used. So video-based, as I said, there you can also use this compression and also the loss that has been generated. And compression is an issue with detection, because this is often used when uploading images to YouTube or social media, and makes it more complicated to detect those deepfakes. There are many databases, so Celeb deepfake you might download from the internet. And this is one of the most challenging sets of deepfakes that we saw. Deepfake detection challenge is less real, and of course it's best to have real world data, because that's the kind of data that we also will receive in real cases. So there are several models, and I will not go into detail on all models, but nowadays we see that EfficientNet B7 works quite well according to the literature. And it's available pre-trained on the ImageNet. And we see also in the challenges that this performs best, at least that they have an accuracy of around 84%. So the take-home messages I would like to give is making good deepfakes is getting easier each day. Detecting those good deepfakes is getting more difficult. The chain of evidence is important. And of course, in the past, we are also used to photoshopped images. So for video, this should be similar. And we also have several publications that you might want to read about this topic. I would like to thank you very much for your attention. And if you have any questions, I would be happy to address them. So you can send me an email on this. Okay, thank you very much.
Hi everyone, this is Aoshen from the University of Hong Kong. This research is done by Dr. K.P. Chow and me, and our title is Feature Extraction of Protest Demonstration on Linden Discussion Forum. Here is the agenda of this presentation. We will first overview the Linden dataset, then talk about the motivation of this research. Then it is the experiment on multi-label classification. Finally, we'll have a conclusion and talk about the future work. In today's cyberspace, many cybercrimes leave traces in social media platforms, such as Facebook and online discussion forum. And potential criminal activities may be posted in social media. In this way, the online platforms are the places for detecting potential crimes and obtaining traces. The Linden Discussion Forum is a well-known multi-category discussion forum in Hong Kong. Some activity organizers will post notification messages in advance, and the supporters or regular users can immediately read, participate, and post their comments. From August 2019, most of the discussions on the forum refers to public gathering and demonstrations. The demonstrations in Hong Kong over these past months have astonished the world. But whether a particular activity constitutes a criminal offense depends on the local laws and regulations. But it is still important in police resource management to identify the features of an unregistered demonstration. So this study established a model to automatically identify the features of the demonstrations from public posts. We divided our experiment into 4 parts: data collection and labeling, the post vectorization, multi-label classification model, and finally is the experiment result. The first step is data collection. We collect the posts on Linden Current Affairs section from 2019 August to October. Most of the posts are in traditional Chinese or Cantonese, and the sentence in this bracket is the English translation for this presentation. About data labeling, totally there are 7 labels: strikes, arson, wounding, sit-ins, parades, riots, and conflict. And we randomly select 1,272 posts to label the data like this, like the table shown here. The second part is the post vectorization. We first use a doc2vector method to transfer the textual posts to vector matrix, and then use the Pearson's correlation coefficient to calculate the coefficient matrix to find the relationship between the post and the 7 labels. And then this matrix is the input of the multi-label classification model. For the classification model, we use MLP, the neural network, to build the model. It is a class of the feed-forward artificial neural network. And I show the structure and the information of the model here. The accuracy, precision, recall, and F1 score are shown in this slide. And from the weighted average value here, we can see that MLP has a good performance and reliable classifying to the corresponding labels. But since the label data is unbalanced, it's still difficult to identify some minority features. We can also output some high correlation topics appear in each class. So based on these topics, it is feasible to describe the subject and understand the urgency of the corresponding demonstration. To make a conclusion, the fluid demonstration will not only disrupt the business and traffic, but also affect social security and threaten the social order. We use MLP multi-label classification methods to understand the specific forms and the characteristic of the harmful demonstration on online forums, so that it can provide the theoretical support and application examples to assign resources and have a proper monitoring of the activity schedule. The future research will attempt to study the relationship between the subjects and discourses on a deeper level. And that's the end of this presentation, and thank you for your listening.
The calibration of step count logs in Apple Health data. We compare the Apple Health database step count logs with the acceleration and rotation characteristics, which constitute a robust step identification to create a controlled step test rig to adjust metrics such as lag, bias, and aggregation through 3 distinct experiments which consist of different step intensities and durations. The results from experiments 1 and 2 overlap, showing the lag present in the step count logs. Likewise, experiments 2 and 3 overlap, showing the bias present in the step count logs. And experiment 3 highlights the aggregation of step count error. The first experiment consists of the rig performing 60 steps, pausing for 17 seconds, and repeating 10 times. The first observation here is that Apple Health records these as 58 steps. In MATLAB, we superimpose the Apple Health logs in blue over the activity accelerometer measurements in red. Here, the step interval initiates at 32.0 seconds, while the watch logs the step interval 7.0 seconds later, allowing for time synchronization differences of plus or minus 1.0 seconds for the activity data and plus or minus 0.5 seconds for the Apple Health log data. We apply a combined error of plus or minus 1.12 seconds to determine a measured time lag of between 5.9 and 8.1 seconds on this first sample. The last step concludes at 63.7 seconds, with the Apple Health log stopping at 65 seconds. This is a time lag of 1.3 plus or minus 1.1 seconds. Importantly, the acceleration interval, including attack and decay, is 31.7 seconds. But the Apple Watch reports a biased interval of 26 seconds. This table shows the variation in lag times across the 10 intervals, reference to an experimental time clock initiated 39 seconds before the first Apple Health interval log. Note that we start to see the start lag get smaller over time and the end lag get negative. This might be a sample period bias or some sort of clock shift. We need to review carefully in future experiments. We want to calibrate our clock to millisecond accuracy. The sharp attack or rising edge of each sawtooth in this figure represents the start lag, while steps accumulate before the step interval start time is logged. The shortened step log interval compresses the step rate, so that once the interval starts, steps are counted at a faster rate than excitation, effectively catching up and reducing the count bias. We see a compressed time interval catching up with ground truth. In the second experiment, we ran the apparatus for 150 minutes in 4 long intervals, 3 of 14 minutes with 1,680 steps each, and 1 of 75 minutes, which is about 9,000 steps. The purpose here is to see how long intervals behave. It can be seen that the error in the step count does not show a clear positive or negative bias. There are spikes at the beginning of each time interval, but eventually it catches up. If the short-term transient bias caused by the lag between initial step excitation and the log initiation is excluded, it could be seen that the cumulative error in this experiment lies between plus 13 or minus 8 steps over a total of 14,040 steps, or a cumulative error of 0.1%. We see a relatively high error for any given interval, but over the day, it looks like it balances out. Here for experiment 3, we see many step intervals not terminating correctly. In Apple Health, unlike the previous cases, where it aggregates many step periods into singular larger periods. Of particular interest here is that the first measurement interval shows 708 steps, capturing a total of 720 steps over a 510-second interval. Although the instantaneous step rate is 2.0 steps per minute, the inclusion of the 5 30-second rest periods means that the reported average step rate over 507 seconds is actually 1.4 steps per second. There are many limitations with our preliminary results. For example, we attempted to reduce the delay between consecutive step intervals as low as possible until the Apple Watch could not differentiate the gap and write different step periods as a single log. Multiple tests seem to suggest this around 15 steps or around 7.5 to 8 seconds of activity at our current settings. However, repeating this experiment did not always reproduce the same result. Some of the experiments stopped being able to differentiate the intervals even with a 2-minute break in between. Thank you for listening to my presentation.